So let's see. Can you see anything now? Oh.
No, not yet.
Not quite yet.
Interesting. Well,
you've started screen sharing, but it's blank, at least for me.
Okay, well, what I will do is just share from my Mac. So I won't be doing as much writing. At least this should work, I think. Just give me a moment. All right, so that I hope you can see. And it is quite an honor to introduce Patrick Lee. He's a very recognized condensed matter theorist. I will say a tiny bit about his work in a moment, but he recently retired, at least on paper, from MIT, where he spent the second part of his career. The first part was at Bell Labs. He's been recognized with the Buckley Prize, membership in the National Academy of Sciences, the Dirac Medal of ICTP, and various other things that I won't go into. What might be even more impressive is that for a little bit over 4 decades, Patrick has really been at the forefront of condensed matter theory. I don't think that's an exaggeration. Going back to work on mesoscopic physics like weak localization and universal conductance fluctuations, then high temperature superconductivity, and then more recently, spin liquids and topological superconductors. And the last is what you'll hear about today. Something he may be less excited about credit for is that he also influenced several generations of graduate students at MIT. Many of us, not just in condensed matter, but in other fields, learned solid state from Patrick. So his influence is really quite broad, even beyond his research. And I certainly am in that category of people who sort of learned, at least to whatever extent we learned it, people who learned how to think like a modern condensed matter theorist from Patrick. So with that, let me dive in. And what we decided to do, the focus of Patrick's talk will be on a very new and exciting kind of quasi-particle in solids called the Majorana zero mode. I'm going to explain what is a quasi-particle and what is a topological phase with some of the historically important examples that kind of come together in this Majorana zero mode. And I realized that within CIQC, and just looking at the names here, we have everything from people for whom this will be pretty familiar to people who have not thought about a solid maybe ever. So I'll do my best, but please ask questions either now or it's great that we have extra time for discussion. I'm going to start with a few pictures and then I only have a couple lines of mathematics toward the end. And the pictures may be dissatisfying, but yeah, you could always take a course or read a book or ask me offline and I would be happy, very happy to tell you more. So first, oops. The field of topological phases, of which these phases supporting Majorana zero modes might be the most spectacular example, began in 1980. And it began in the lab with a fairly standard condensed matter experiment, which is you take a solid and you apply a magnetic field and you run a current perpendicular to the magnetic field that gets deflected by the field. And then you measure the voltage that builds up proportional to the current. And when you do that, you can convert it to a conductance, if you like. It's a transverse or Hall conductance. And you find that at weak magnetic fields, it's a straight line. And we usually use this to figure out how many carriers there are in a solid and whether there are electrons or holes. As you go up to larger magnetic fields in two-dimensional systems, you find something pretty amazing, which is these plateaus. And in fact, they're not just flat to the resolution of the screen. What you're measuring on these plateaus is basically E squared over H, this ratio of some fundamental constants to about 1 part in a billion. And that means, just for the atomic physicists out there, that when you call solid state physics squalid state physics, or say it's messy, or it's got dissipation or phonons or whatever, that's not always true, because this is some big chunk of matter, and yet it manages to be perfect on a macroscopic scale. And that's because you're asking the right question. Many things in a solid are messy, but if you measure the right things, they might be sort of topologically perfect. And the big challenge that Patrick is going to talk about steps toward is how can you make a quantum computation one of these right questions where you get the answer to very high accuracy because of topology.
Oh, just one, sorry for interrupting. There's the bottom right of your screen there's this colors bar that basically is blocking the bottom right. I don't know if other people can see it. It's not blocking, but if it's easy to, yeah.
I don't know how that happened, but I think I can get rid of it.
Yeah, there we go. I think that'll.
Thank you for pointing that out, and let me get going again here. All right, so I can't really give the full magic of where that topological protection comes from, but I can say one thing about it, which is going to be relevant to what comes up later, which is if you just look in the middle of one of these quantum Hall samples, it looks pretty much like a two-dimensional insulator. It has an energy gap and there's not that much going on. But it turns out that wherever you go from this insulating state to an ordinary insulator or vacuum or whatever, there's always a special metallic region in between, which we call the edge. And the fact that the bulk topology forces this edge state to be there is called the bulk edge correspondence. And in particular, for the quantum Hall example, it is a one-way street. There is a sort of one-dimensional wire at the boundary of the sample where electrons can only move in one direction. And because they can't backscatter, it conducts basically perfectly, like you saw in the previous slide. So this edge state is one example of what topological protection looks like. If you want a very rough picture of what's going on, the idea is that the wave functions are wrapped up inside the sample. This is just the wave function of the block electron in a solid, but it could have some non-trivial topology that you can't destroy without some drastic change. And the wave functions are not knotted up in the same way outside. So something drastic has to happen, which in the topology of knots would be like cutting the string. That's like cheating. The way you cheat in a solid is that you close the energy gap and have a metal. Now, the kind of state that you're going to hear about later is a superconductor that also has an edge state, but one of the things that moves at the edge is a new kind of particle, the Majorana fermion, or we shouldn't even really call it a Majorana fermion, we should call it a Majorana particle or Majorana zero mode for reasons I'll talk about in a second. But first I want to say, why would you get things other than electron? What is this quasi-particle idea? And there, the brief history is that after people found that integer Hall effect, first example of topological protection, they found other examples in these two-dimensional systems in strong magnetic field where actually the electron breaks up. In the simplest case, the electron breaks up into 3 charge E/3 particles. And we thought we understood things pretty well for a while, but then something even more exotic happens in those states labeled under group 3. And it turns out that's very hard to confirm experimentally in these quantum Hall systems. We might have better hope of seeing something like this in superconducting systems. But then I need to tell you a little bit about the theory of superconductors. But the big surprise is that when you go into a solid, you might think a solid is made of electrons and the ions are usually just sitting there. So all you have are electrons. And to start with, that's true. But the idea of the quasi-particle is that what might actually be the stable excitation of the system at low energies that you see moving around doesn't have to be an electron. It might not even have the charge of an electron. It might have not even bosonic or fermionic statistics if you're in 2 dimensions. So I'm going to give you one example of a non-trivial quasi-particle to lead into Patrick, which is the ordinary quasi-particles of ordinary superconductors. But even these ordinary quasi-particles are pretty remarkable. But just as a simple example of a quasi-particle, when you're in a normal metal or even in the integer Hall effect, the quasi-particle is, we would say, basically an electron or adiabatically connected to an electron in the following sense. If you took an electron and you surrounded it with a cloud of electron-hole pairs, you might change its effective mass, but it would still have the charge of the electron because the electron-hole pairs are neutral, and it would still have fermionic statistics. So in ordinary metals, the reason why we call them Fermi liquids is that even as you crank up the repulsion between the electrons, you still have electron-like quasi-particles. Maybe one difference from the vacuum is that you have holes, where a hole is you had an occupied state in the ground state, say a filled band, and you took one electron out of that acts like a quasi-particle with opposite charge to the electron. It's like the solid state version of a positron. And as I mentioned, there are cases where the electron breaks up. But let me talk about what I think was the first really shocking quasi-particle to be understood, which is in a superconductor, because I think Patrick's talk is going to focus on how you could make Majorana zero modes in some kinds of superconductor. And here, I would say the field of quantum materials or strongly correlated electrons, whatever you want to call it, started a little bit more than 100 years ago in Leiden. Kamerlingh Onnes managed to liquefy helium and get to what were then low temperatures. They're not picokelvin, but they're pretty low by most people's standards, a few Kelvin. And he realized that with some metals, when you cool them down enough, the resistivity basically falls off a cliff. So why that happens took about 50 years to understand. It took the beginning of, I would say, the theoretical understanding of complicated quantum materials by Bardeen, Cooper, and Schrieffer. the so-called BCS theory of superconductivity. And what I want to focus on is, what does that theory predict about the particles in a superconductor? So you probably have heard that it predicts things like pairing of electrons and so on, which are spectacularly confirmed through things like the Josephson effect. But I want to talk about another aspect that you might not have heard about, where you can see how it's a little bit like what happens in an ordinary metal, but with a very exciting set of changes. So in an ordinary metal, let me draw the radial direction of momentum k and think about energy as a function of k. So normally you would think maybe about energy going as h bar squared k squared over 2m. What I've done here is just linearize near the Fermi surface, because if we're at low temperatures like a few Kelvin, we're going to be pretty close to the Fermi surface for most purposes. So normally you would think about energy maybe starting from 0 and going up, but we're going to define the 0 of energy to be the Fermi level. And then we've got an interesting situation where there are some occupied electroned states, that's the dotted line. But I want to think about those as already filled in the ground state. So if I'm thinking about excitations above the ground state, I could take out one of those electrons and that would have positive energy. And that's this whole branch on the left. So I've got a whole branch, which are excitations above the ground state, so they have positive energy. And I've got an electron branch at momentum larger than the Fermi momentum, which are just ordinary electrons. So what happens in a superconductor? Well, the superconductor dispersion relation is that smooth line at the top, where now a couple of things have happened. So I left the metal lines just for comparison, but with the superconductor, that top curvy line, the idea is that now there's a quasi-particle excitation that, first of all, always has an energy gap. It never goes to 0 energy. And second, it goes smoothly from electron to hole, which sounds perverse because an electron has negative charge, 1, E, minus E, I guess, and a hole has positive charge, E. So how could I go smoothly from plus E to minus E? And the answer is, there is a certain kind of quasi-particle that if I'm far away from the Fermi surface, looks like either an electron or hole, but manages to go smoothly from hole to electron as I increase the magnitude of momentum. And this Bogoliubov quasi-particle, I'll write down a little bit of math in a second, but if it's hard to get all the details, I think, in a quick introduction. The takeaway is that you can superpose electron and hole, and then you have a particle which has variable charge, but it's still an ordinary fermion. So that smooth curve I drew of excitation energy, mathematically in BCS theory, is something like this top line, this square root. It's the squared energy difference from the Fermi level, that's the left term, plus something that gives me a gap even when I'm right at the Fermi level. But then what kind of operator should I apply to create one of these quasi-particles? And what's written in the second line are the Bogoliubov fermion creation and annihilation operators. And if I look at the creation operator on the left, for example, that is a combination of create an electron with one momentum and spin up, and then annihilate an electron, or if you could view it as creating a hole as you like. So this has a well-defined momentum and a well-defined spin, but it does not have a well-defined charge. I basically have created a quasi-particle that goes smoothly from electron to hole. But these are still ordinary fermions in the sense that they're what we call complex fermions because the Hermitian conjugate is not the same as the original operator. And in terms of commutation relations, if you like, they're like the same fermions that we normally deal with. But there is another possibility that doesn't happen in ordinary superconductors, but we think might happen in some interesting ones. And the mathematics of this was maybe pointed out by Majorana in particle physics a long time ago. And the point he made was, this is in the early days after Dirac's theory of the electron. And the main prediction of the Dirac theory experimentally was that in addition to the electron, there is an antiparticle, the positron. So Majorana's point, and the title is something like Symmetric Theory of the Electron and the Positron, is that you could have a situation, this wouldn't work for the electron, but maybe it works for some other particles, where some fermion, say, is its own antiparticle, meaning that if I brought two of them together, they could annihilate each other because anything can annihilate its antiparticle. And we still suspect that such particles do exist in nature. The neutrino would be an example. It's not clear yet whether the neutrino and the antineutrino are different particles. Note that the neutrino is neutral, there's no simple additive quantum number like charge that lets you distinguish the neutrino from the antineutrino. So people are looking for that. But what happens in condensed matter, even though the mathematics of the operators is a tiny bit similar to what Majorana was talking about, the physical meaning and the energy and things like that are very different, which I think will come out in Patrick's talk. But I wanted to say one more piece of the theory of superconductivity that will give you a clue to where you might find something special that is like half of an ordinary fermion, and then just write a couple of equations for what that means to be half of an ordinary fermion, and then I'll hand over to Patrick. So here, suppose you wanted to figure out, in a situation more complicated than just a perfect translation invariant crystal, you wanted to figure out what are the states of these Bogoliubov fermions. So the way you do that is something called the Bogoliubov-de Gennes equation. But you might ask, well, how mathematically can I write energy levels that encode variable charge or both positive and negative charges? And it turns out that when you do that carefully, you wind up with an interesting sort of Hamiltonian that has a particle hole symmetry, we call it, where every time there's a level at positive energy E, there's another level related to it at negative energy minus E. And then to get back to the physical world, we sort of have to take half of the spectrum that appears in this mathematical approach. So a particle hole symmetry is like a relationship between plus E and minus E, and one ordinary fermion is represented in Bogoliubov-de Gennes spectrum by a pair, by one state at E and one state at minus E. But then you realize, there's one special thing here, which is zero energy is equal to minus zero energy. There's something special about the E equal to zero line. That's the only energy where I could have one level that is its own pair or is not part of a pair with another level. And that would have to be a very strange object. It would have to be, in a sense, half of a normal fermion, because a normal fermion is represented by two levels in this approach. So what would be represented by one level? And that's my last slide, which is the following idea. So it should be half of a normal fermion, and a normal spinless fermion, like a two-level system, would be represented by, let's say, C and C dagger. Those are just the operators that either take empty to occupied or occupied to empty. And one thing we usually teach is that the simplest non-trivial quantum mechanics you could have is the two-level Hilbert space that we would use these operators to move around in, the creation and annihilation operator. But the point of the mathematics here, and these gamma operators are Majorana operators, or Majorana fermion operators. The magic is that these gammas are equal to their own Hermitian conjugates, and I can make two of them, gamma 1 and gamma 2, out of the real and imaginary parts, in a sense, of the Dirac fermion operator. So a Majorana fermion is half of an ordinary fermion. And that creates some interesting possibilities. Maybe you could store some information which you'd normally store in a two-level system or one spinless fermion as two of these Majorana fermions. And here's where a subtle thing is that these Majorana fermions, that's a bit of an abuse of language, because the operators that I've written here are like what Majorana was talking about. But the way that Majorana fermions actually move around each other is an even more dramatic example of something I mentioned earlier, which is that in 2 dimensions, particles don't have to be bosons or fermions. They could actually be other things. And the Majorana particles that Patrick is now going to talk about are not actually bosons or fermions. They're something else. They have a very unusual kind of particle statistics. And one of the highest priorities in the field is to find evidence for that. So already you can see from just this simple bit of writing that, well, maybe you could store one qubit, one two-level system as two Majoranas and put them in different places. But then the question is, what could you do with them? And the picture at the bottom right, which is from a Scientific American article, where if you like, you could read more, is the following idea of what these Majorana degrees of freedom might be useful for. So the way I started the talk was to say, solids are not messy if you ask the right question. If you ask about the Josephson effect, or if you ask about the integer quantum Hall effect, they're not messy at all. They do what they're supposed to 1 part in a billion or better. So if you could make these Majorana particles and move them around each other in the right way, it turns out that that would let you build a kind of quantum computer where, in a sense, the answer is one of these topologically protected right questions. So how exactly that happens, how do you get from some set of Majorana particles to something you might actually measure? And first of all, how do you make these Majoranas in the laboratory? I think for that, I'd better hand over to Patrick. So I am going to try to stop sharing here.
Okay, can I try to share now? Okay. Okay, does it work?
Yes.
Okay, very good. Well, thank you, Joe, for the very nice introduction. Makes my job much easier. And of course, it's a great pleasure to be speaking to this group today. I was told the audience is very diverse, and but I think Joe really broke the ice for me. Yeah, so I want to talk about Majorana, and I purposely make a point in the title of calling these things Majorana zero mode, because as Joe already alluded to, we really shouldn't call them fermions. They really, what we have in mind is really different from even a neutrino that people have in mind. So I want to make a distinction between sort of neutrino-like objects in Majorana zero mode, which is our, what we have in mind is something actually very, very special. Okay, so so my plan is to ask a number of questions, starting with what they are and why are they interesting. And so the point is that two of these, I'll call them MZMs, Majorana zero modes, encode one fermion, but in a non-local way. And so this leads to so-called braiding statistics that I'll explain, and the proposal to use them to build fault-tolerant computers and qubits. And then next, I would want to address the question of where would you find them, now that we theoretically think they exist. And so they are invariably tied to topological superconductors, and I'll explain what they are. And so the places you would look is either in a vortex core of a topological superconductor, or at the end, if you can make a strip of a long strip of a topological superconductor, you can look at the ends, and they're supposed to be living there. Well, the next question is, how do you detect them? How do you know they're there? And then how do you measure the key property? And I'll emphasize this property called Fermion Parity. And that turns out to be the number that really characterizes them. And it is the thing that we want to measure if we want to turn these into qubits. So stay focused on this notion of Fermion parity, which I'll, of course, I'll explain as I go along. And then I'll show some examples where they may have been found. I think there are evidence that they may be popping up in a variety of places. And I would then go on to describe a roadmap to create qubits based on these Majorana fermions, zero modes. And I'll describe the route to quantum computers, which I think the current thinking is not ones that are based on braiding, but rather measurement-based quantum computers. And I think people realize that braiding is too hard, but there's something else we can do, which is no less spectacular. And finally, the burning question of the day, right? When will we know for sure that we have found them? When will we make a qubit? When will I order one from Amazon by mail order? Right. I don't pretend to answer all the questions today. There are some very good reviews by Jason Alicia and Carlo Benica that covers the basics. Okay, so let me start with a little formalism. If you don't like formalism, you don't have to pay attention to this first slide. But sometimes, so let me just start with a somewhat formal definition of our operators. So, okay, there's my pointer. Let me find my pointer. Can you see my pointer? Ah, okay. Laser pointer. Okay, very good. So for fermions, we talk about creation and destruction operators. So this just means that we destroy one fermion, and here we add one fermion out of the vacuum, and they satisfy this anti-commutation relationship. Okay, and formally, you're always free to write these fermion operators, which are generally complex operator, decompose them into the real and imaginary part. So this is just completely formal definition. And each individual one would be real operators, which means that that complex conjugate is itself. Okay. And then, of course, you can invert that, and you can see that the gamma 1 is just a sum of the F and F dagger, and gamma 2 is minus I times F minus I dagger. So both of these, of course, are real. Okay. And now if you work through from this anti-commutator, you will realize that these gammas also satisfy anti-commutation relation. Different gammas anti-commute, but the same gamma, there's an extra factor 2. But since if gamma is the same as itself, you see, this doesn't work here. So now, because gamma dagger is the same as gamma, that means that gamma square is 1. Okay, so this is a very different object than what we started with originally, because for fermion operators, F square is 0, right? Because you cannot kill a dead horse, right? Because you've killed the fermion once, and then you try to kill it again, right? You cannot do that, right? So F square is 0, but here gamma square is 1. Okay, so that makes a big distinction, because I think this goes back to our understanding of the Hilbert space, or actually Fock space. But for usual fermions, we always draw a line, okay, at any energy. We say that there's a state at that energy. And then we say that, well, this state can be either empty, there are no fermions, or they can be occupied. So there's one fermion sitting there, okay? And we can count the number of fermions, which F dagger F is 0, F dagger F is 1 here. And then, of course, F squared is 0. But, and this is something I want to emphasize very much, we must abandon this notion if we ever find a Majorana zero mode, okay? So you can still draw a line at energy 0 to denote that you have a state at 0 energy, but we cannot think of this line as a state where you can either occupy or unoccupy them, right? Such a notion cannot make sense, because if I occupy it, how is it that I occupy it again, I get back to where I started, okay? Right, so this we have to abandon, I emphasize that, we have to abandon this notion of Hilbert space for Majorana, okay? Now, of course, this is just math. This is a trivial math, and anybody can do this. And formal decomposition is usually boring, because it doesn't give me any new information. So just formally, you think that, oh, I have these neutral objects. But in practice, this gamma 1 and gamma 2 usually exist, overlap in space. They live in the same place. And so this is just a complicated reformulation of something very simple. Okay. Now, the interesting question arises, what if we can find a discrete fermion eigenstate? Namely, I want an isolated one, a discrete state, so that the corresponding gamma 1 and gamma 2 somehow arranged that they live far apart in space, okay? And that takes some doing, but in principle it's possible, okay? And then I would argue that in that situation, we have something interesting, okay? And that situation we call a Majorana zero mode, all right? And from Joe's discussion, you can see that superconductors are the natural place to look for Majorana fermion, because they are superposition of a particle and whole. And the superconductor is the place in solid that allows us to do that. Okay, so then let me start by explaining to you what the superconductors are. Okay, superconductors are both condensation of Cooper pairs. And let me, for simplicity, just talk about a spinless case. So we pair a pair of electrons on this is a Fermi surface in momentum space. So ordinary metal has a Fermi surface fully occupied inside. So a superconductor is one where we take an electron outside at momentum k and one at minus k and form a pair, okay? And then we can write a pair wave function, which is just the creation of these two objects, okay? So this wave function has the notion of making a pair out of the vacuum, okay? And I think atomic physicists are familiar with Bose condensation. We think of this as a boson, a pair fermions behave like a boson. And so this is a coherent superposition of pairs, and that's what makes a superconductor. Okay. Now this wave function can be k-dependent in general. And the amazing thing about a superconductor is that the ground state is a coherent superposition of pairs of these objects, just like a boson is that. So the only thing we need to know about a superconductor for today's talk is the following: that if I have a block of superconductor, it costs me no energy to add a pair of electrons to the ground state. Okay, and that's because this is already a superposition of many pairs. They don't care whether you add one pair or not. All right. And in fact, if a superconductor has a fixed phase, it actually has a undetermined number of pairs. Okay, so that's one important piece of information. It costs me nothing to add a pair. But if I want to add a single electron, then it costs me an energy gap, which is actually related to this thing somehow. Okay, so that's all we need to know. And mathematically, BCS first wrote down this Hamiltonian, which is, if you generalize it, it's called a Bogoliubov-de Gennes Hamiltonian. It measures the electron energy relative to the chemical potential, which is appropriate for an electron. And it measures the Hall energy, or negative of the electron energy, which is appropriate for Hall. So we can think of this as a 2x2 matrix, and they are mixed by this off-diagonal order parameter, delta. And if you solve that, you get the solution, which is the Bogoliubov quasi particles that Joe explained. Well, you may be bothered that how can I mix electron destruction operator and the creation operator? They have different fermion numbers. Right? We know that we have to conserve fermion number. Electrons don't disappear in midair. And so the answer is that you should really put a operator P here, which is exactly this P that adds a pair to the ground state. Okay. Once you have this P here, then we can understand that the Bogoliubov operator actually preserves particle number. Okay, because I remove an electron, or I add an electron, but at the same time I remove a pair from the ground state. Okay. So if you go back and look at, for example, Josephson's original paper on Josephson junction, he had this P in his definition of the Bogoliubov operator. It's just that over time, solid-state physicists have gotten lazy, and we no longer write down this P. And so things looks mysterious, but in fact, it is not at all mysterious. The quasi-particles have a fixed number. We just have to remember that we can always add and remove a pair at will. Okay. Okay, so now let's talk about counting states. So let's start from something simple, which is of metal. A metal is a fermion. Let me just draw a one-dimensional spectrum. And the states below the Fermi energy, this is chemical potential, are filled, right? So we call it a filled Fermi sea. But Landau taught us a long time ago that we shouldn't think about, when we think about any physical system, we should think about a ground state and then excitation above that ground state. So we should always think of adding energy to make excitations, right? Because the ground state can be very complicated, but it's basically dead, right? So it's not important for us to understand the ground state. It's more important to understand the low-lying excitations. Well, for the metal, the ground state would have an electron branch where I can add an electron here, but it has a Hall branch because I can remove an electron from here, right? So if I remove an electron, I can call it a Hall, and it has the opposite quantum number and so on. Okay, so this is how we draw it. And so this is very nice because now all the energies are positive. And so these are all excitation energies. I can make an electron excitation or Hall excitation out of the ground state of a metal. All right. Now, if you are somewhat devious-minded, you might say that, okay, this doesn't look very symmetric. Let me just double my representation. Let me just extend this line below and extend the red line below, right? So I can just, this is a redundant representation, right? You can see that now I have double the amount of states that I had before. Now you say, why do I want to do that? Well, the reason why we want to do that is that in superconductivity, you are pairing these electron and Hall state. Again, keeping in mind that you have a hidden pair there. And so this allows us to think in terms of something that we're more familiar with, namely hybridization of two energy levels, right? If you have two energy levels and you have a hybridization, then you have level avoided crossing, and you can immediately see the spectrum looks like this. Okay, so if you do the math, and this is the answer, you solve this Bogoliubov the Hamiltonian, your eigenvalue is exactly just the diagonal component square plus this gap square. So this explains immediately why the energy gap is here. But notice that the energy eigenvalues always come in pairs, plus or minus. And some of you students may have wondered, why do I get a negative energy? You know, I should be looking for excitations. What does a negative energy mean if I already have a ground state? Okay. Well, the answer is that this is kind of fake, because this negative energy really comes from my my trick of doubling my representation. And so really, I should just forget about the low lying ones, and the physical excitations, the positive energy ones, are the physical excitations. Okay, but you can see that the fermion is a linear superposition of electrons, a pair, and a creation operator. Okay, now you can. It turns out that these energies always comes in plus or minus pairs. So I can also label the eigenvalue, the eigenvector. The eigenvectors have this relationship that they are not independent. They are complex conjugate of each other. Okay, so that's is very reasonable, because I have double my degrees of freedom. So these guys are really not independent of these guys. Okay, and so it's fair for me to say, to make the following statement, that only the positive energy excitations above and some gap are physical. These guys are kind of non-physical, but in this picture, it took two of these fermions to represent one Bogoliubov quasi-particle, right? Because they always are double, right? So it's very strange. In this BCS theory, really, I have to draw two lines to represent one state. But in a way, it's not strange, because if you just look at this, you know, we have more degrees freedom than we started with, right? Okay. Well, now you can ask the following question: what if, right? What if somehow I can find a state that sits in the middle at zero energy, right? So at this point, it's daydreaming. You can say that suppose you find a state. Well, this state would have some rather amazing property, right? Because it is at energy zero, and according to this description, plus energy and minus energy are not independent, so it will be a complex conjugate to each other. So this one must be a real fermion, which fits our definition of a Majorana fermion. Okay. Furthermore, this is at energy zero, so we call this a Majorana zero mode, and it has to be unique. It has to be one. Okay, that's the condition. It has to be just one of them, not two. Okay. Now, the reason I want it to be one is that if I have only one state, then this state is absolutely stable. Okay, think about that. In terms of eigenstates, usually I can move them around by putting a perturbation. If I bring another charge near my electron, this state is going to move up and down in energy. But this one cannot move. Why can't it move? Because as long as it moves away from zero, it has to be two states, right? Because it's Hamiltonian has particle symmetry. Okay, so one state cannot suddenly become two states. So no matter what you do to it, you can hit it with a sledgehammer. It's going to stay at zero energy. Okay. Now, of course, I kind of cheated, because I declared that I have only one state here, right? That's why this works. Okay. But keep that in mind. So should we think of this as half of a fermion state, right? So this state is not something that I can think of as being occupied or empty. It's just there in the ground state. Okay, right. So that's kind of my motivation for this Majorana zero mode. Okay, let's go further. So we know that such a mode cannot exist in the homogeneous superconductor, because the way I set up the problem, the electron states always come in pair, plus or minus. I cannot have a single one. But we could imagine having such a state in a homogeneous, on the boundary of a topological superconductor. Okay, Joe has already explained to you that on the boundary of any topological state, you expect an edge state which goes through zero energy, because the energy gap must close. If it's a gap state inside, gap state outside, to go from non-topological to non-topological, the gap must close, right? Because otherwise, I don't know when I left being topological, right? So that's the good thing about topological. It's either 1 or 0, right? You cannot have something in between. So as a general theorem, there must be a 0 mode on the edge. And it turns out that if you have a topological superconductor, you have a Majorana mode instead of a Fermion mode that propagates in one direction. Okay. Now, so for then in our search, we need to find a topological superconductor. Right. So let's just consider the simplest example of a topological superconductor in 2 dimensions. And this is the so-called P plus IP state. This is a state where the pair wave function takes this form, P plus IP, or in other words, if you go to a radial coordinate, it has a phase winding where theta is the angle in momentum space, right? And has a bulk. So this thing has a bulk gap. The energy gap is non-zero, but the wave function winds. Now, where does the topology comes from? Well, again, I'm repeating this BCS Hamiltonian. It has this diagonal term and an off-diagonal term. Now, any 2x2 can be written as in terms of the Pauli matrices, the 3 Pauli matrices. We can decompose it into a vector with 3 components. Now, this vector now has the following property. If you are inside the Fermi C in the middle of the k equal to 0, is pointing down. Why? Because deep inside the Fermi surface, this is negative. The state is way below the Fermi energy. This is positive. So this looks like in minus number times z, right? So therefore, it's an arrow pointing down. Way outside, this is positive, and this is negative. So outside is up. And in between, there's this off-diagonal term. If this delta is real, then this will be a component in the xz plane. So this vector k will be rotating if I go from inside the Fermi surface to outside the Fermi surface like this. All right. Now, if this were P plus IP, there's a phase winding. So if I move in different radial direction, now this thing becomes complex. So complex means that a y component kicks in. So this phase will now pick up a y direction, right? So the picture is that if I go in any direction, then this thing is actually pointing along that direction. So this is a picture. If I go this way, I get here, this way, like this, okay? Now, so this thing is topological. And the reason you can see that is that if I mathematically identify the infinity with a point, then this disk will wrap up into this surface of a sphere. And then these arrows will become hedgehog, right? You kind of see that, right? The one in the middle is pointing down. This is k equal to 0. The one at infinity is pointing up. It's the North Pole. And in between, it smoothly connects. And so it's like it's a hedgehog. Now, hedgehog is topological. We cannot get rid of these arrows smoothly by deforming. Okay, so this is the reason why this is topological, right? So this thing is happening in K space, and this vector is a pseudo spin, is not a real spin. If this were a real spin and this is in real space, this is what people call a skyrmion. And this thing has the same topology as a skyrmion. And this is why I can download nice pictures from the internet to show it to you. Okay, so now we're almost there because this thing, now if we have this superconductor, on the surface, there has to be a mode. Let me drill a hole in the middle. Okay, let's see if I have better luck. If I drill a hole in the middle, if this hole is very small, this just means that the discretization energy is bigger. I still have no zero mode. So for the final trick is to put a vortex in the middle of this hole. Right? A vortex is nothing but a winding of the superconducting phase by 2 pi. Okay. Now, if you wind the superconducting phase by 2 pi, that basically undo this original winding that is in your wave function. And now I have a periodic boundary condition. And now this 1/2 is gone, and I have these discrete state, and I have my zero mode. Right? So this is a little long-winded way to show you how I can actually get a zero mode, which is a single isolated zero mode, right? The isolation is important because it's only on the surface of the topological system that I have one mode. Otherwise, I generally will have two modes. If I have two modes, then I'm defeated again. But now you can see, in fact, I have two zero modes in this finite system, which satisfy my requirement. The eigenvalues also always comes in pairs. But one of them is living on the outer edge, and the other one is living on the inside edge. And this inside edge can be actually arbitrarily small, can be a very small object. So I have also accomplished my goal of keeping them separate in space. Okay, so this is the message. So in this picture, I also, in addition to the zero mode, I have this continuum of states up here. So these are propagating fermions. Each of them has a minus energy partner. So they are actually ordinary fermions in the sense that nothing magical about them. They're not half a fermion, and they obey fermion statistics and so on. So these could be our neutrino. But these two guys are very special. They are really Majorana zero mode, and they are real. Each of them really should be thought of as half a fermion. Okay, but in a finite system, sanity is restored because I do find two of them. And now I managed to accomplish what I started to do. I have a system where I have discrete and two of zero mode, and they are separately, spatially separated. Okay. Yeah, so now if you understand that, then we can imagine that we have two of these zero modes, right? Two of these vortices. And now we have a zero mode on each vortex, and we don't need one on the edge, right? So, but if I have a third one, then I have one on the edge and so on. So, right. So this is one option. Another option is to have a quasi one-dimensional situation. And this was first shown by Kitaev in a very beautiful, simple one-dimensional model. But we consider that in the following way. So I think this is a useful alternative way of looking at this. We started out a few years ago with through Potter. I started out with a two-dimensional P plus IP superconductor, and this is a plot of the wave function amplitude. Okay, and then we find the zero mode that I described earlier. Now we make this narrow and narrow, and we squeeze down this thing to be a quasi one-dimensional situation. We discovered that this mode that used to go all the way around becomes confined to the end. Okay, so now we have instead of things that are moving all the way around this perimeter, we have modes that are sitting at the end of this thing. Okay, right. So this is another way of getting a Majorana particle. So these will be not particle, Majorana zero modes. They're sitting here at the end. They are spatially separated. I don't need vortices. Okay, and it turns out that they don't always show up. They show up when there's an even an odd number of transverse channel. So as you change the chemical potential, they show up, and then they go to finite energy, and then they collapse and show up and show up. So we call this topological regime. There are regimes where these zero modes appear and disappear. Okay, and we can calculate everything because it's just solving some 2x2 matrix. And I just want to point out, I don't want to go through all the details here, but if you take one of these, see here, we're plotting the lowest energy excited state. This thing looks like it's energy zero, but if you zoom in, its energy is actually not exactly zero. It's just very, very small. It's exponentially small in the separation between the ends in the length. Okay, and indeed there's a partner because the theory guarantees, right? I'm solving the Bogoliubov chain equation. There has to be a partner. Okay, but if I look at the wave function of this almost zero fermion energy, then it can be written as a superposition of creation and destruction operator. But these coefficient turns out to be exactly equal, this U and B. So I mean, and they are complex number. But if I break it up into two complex number, these two wave functions just live on opposite ends. So this is a very surprising thing, right? And so then if you define, I can define this gamma one, which is this wave function times C and D C dagger. So this is one real fermion, and this is another real fermion. And then I reproduce what I started out with, that the fermion operator is a sum of the, it's a gamma plus I gamma 2, as expected. Okay. So this is a little long-winded, but my point is the following. The important message is that I can solve this problem on a computer in a very simple way. And I discover that I find these two low-lying, very low energy excitation. As we discussed before, we should only throw away one and think of this as a fermion. And now this is a honest to God fermion state. I can occupy or empty the state, okay? But this fermion really is represented by two Majorana zero mode. They're living on opposite ends, far removed from space, okay? Right. And so I want to emphasize that mathematically, the mathematics of the Majorana zero mode is actually simple because it involves only fermion bilinear and a 2x2 matrix. Anybody can solve a 2x2 matrix, right? It's not like doing a many-body problem where we don't have a controllable theory. So there are other discussions of fractionalization of particles, emergent particles, spin-ons, and so on, bolons. Those are not well controlled. We don't really understand. But Majorana zero mode are simple object in that context. We have mathematical control of them. We can calculate a wave function. We can calculate what they do if you add impurities. So there's no mystery once you know where to look. So the trick is to know where to look. And this is why I went through this whole long introduction to convince you that you have to look to find some topological superconductor. And once you find them, then you either look at the vortex, or if you look at the end, you would find the zero modes. Okay. By the way, I've forgotten to say that, so keep this picture of the vortex in mind, because I'm going to show you data that I believe actually may be showing this sort of dichotomy. Okay, so I just want to hammer this home one more time. So the story is that we have one strip of Majorana topological superconductors. We managed to make Majorana zero mode at the ends, and they have their own wave function, which is a real wave function. Okay, and out of these two, we have a conventional fermion level, which we can occupy or unoccupy. Okay, and so this is the idea of fermion parity. If this state is occupied, we say that we have fermion parity 1. If this is empty, we say we have parity -1. Okay, so this entire state of affair is characterized by one number, whether this state is occupied or not. We cannot talk about whether this fermion state is occupied, this Majorana state is occupied, or we can talk about the fermion state is being occupied. Okay, so it is in this sense that the Majorana is really half of a fermion. Okay, and information is stored in this fermion parity. Okay, now it's very important to distinguish this picture from a more conventional one that you always know and love. Namely, if I have two well, I have two levels, and then I can make, suppose these stars are being degenerate, then they can tunnel, and I can make, bonding and anti-bonding levels, and I have a wave function that looks like this. It lives on two different places. So you ask, what's the big deal? I mean, I deal with this all the time. I can see this all the time, right? But it is a totally different situation, because here I really have two states. I have two fermion states, right? That are split. Okay. Now in this case, the phase between these two states is very floppy. In other words, because the coupling is exponentially small, I can switch the phase by a little bit. I can twist it. I can change it to plus or minus, and the energy changes only by a little bit. So I can make a complex phase between them. It's a very weak and floppy phase. In this situation, I have only one state, and this is a very important distinction. You cannot think of this as having two different states that are tunnel coupled to each other, right? You're not allowed to think that way, okay? We have to absolutely abandon this notion of states for fermion, okay? So the phase between them are completely locked. This I cannot be changed. This cannot be, it's pi over 2 phase. It cannot be pi over 2 plus epsilon, because I have one state. No matter, I can hit it with a sledgehammer. If I hit it with a sledgehammer, I can change this wave function. I can make this bigger or smaller. but I cannot change this phase. So there's an absolute rigidity between the phase of these two zero modes. Now, the origin of this rigidity is because we're coupling to an underlying superconducting pair condensate, and that superconducting pair condensate has absolute phase rigidity. Okay, so it also goes back to the condensate. Okay, so that's the end of my, so I used most of my time to explain what a Majorana zero mode is, but I think it's okay, right? Because I think once we know what they are, then we can talk, the rest can go rather fast. Okay, so the next question is how to detect them. How do we know they're there, right? Okay, so it turns out that you can actually detect a single Majorana zero mode by tunneling. So now I can take a tip or electrode, I can tunnel electron. So first, let me imagine that this superconductor is grounded, okay? Now, in conventional tunneling, we add or remove a particle from a fermion state, right? Remember, in the conventional, I have a electron state here, so I can add the electron, I can remove from it. And the conductance is proportional to the tunneling probability, right? But I just told you that this thing cannot be thought of as a conventional state. So actually, it is surprising. You may be surprised if I tell you that I can actually see it in tunneling. You know, then the first expectation is that it won't respond to tunneling at all because there's no state for the electron to occupy. But it turns out that nature is clever enough that it uses this Majorana zero mode as a stepping stone. So it uses it as a stepping stone, but the way it can put electrical current to the ground is to take an electron and reject a hole. This way, it put together a pair of electrons. So remember, it cost me nothing to add a pair of electrons to the superconductor. And that pair of electrons can go to ground, okay? So the tunneling process is actually what is called Andreev reflection, where the electron takes this as a stepping stone and takes the electron back out, okay? A consequence of this that we worked out a few years back is that the conductance would have what is called a zero mode. If you plot the IDV, there's a peak at zero energy, but unlike tunneling with a conventional electron, the height of this peak is exactly 2e squared over h, right? So e squared over h is a famous unit for conductance. So 2 is a quantization. This 2 is because what is being transferred is actually a pair, not a single electron. It remembers that you're actually moving 2 electrons. Every time tunnel process, you move 2 electrons. That's why it's 2e squared over h. It knows about the strength of the tunneling only through the tunneling probability or the width of this thing, okay? Yeah. So this is a very unusual situation for tunneling into anything, right? And we suggested that this may be a smoking gun for Majorana's zero mode, not just the fact that it has a zero bias peak, but that its peak height is 2e squared over h. Okay, so I have to confess that I think I bear a little bit of responsibility for the recent debacle about discussion about seeing exactly 2e squared over h quantization. But that's something that we can come back and revisit in our discussion period. Now, I want to say that there's another route, another very important way of measuring Majorana. Okay, so this is just to see one Majorana. Okay, but actually, its most important property of Majorana is not one, but 2. So I want to be able to see 2 Majorana. Okay, so Liang Fu wrote a beautiful paper 10 years ago with this notion of teleportation, and I think it follows very immediately from the picture that I saw before. So we saw that if I have one of these wire, and again, now I want to float it. So it's capacitive coupling. And I want to measure the transmission from one side to the other, okay? Usually, if you have a long wire, the transmission will be completely incoherent from left to right. But I think I convinced you that there's absolute phase rigidity between this fermion, there's actually a fermion sitting here, and there's actually absolute phase rigidity from left to right. So he calls this a teleportation in the sense that the transmission amplitude it's as if there's only one state, even though this wire can be, a millimeter long. It's as if there's one state, so we can squeeze this thing down into nothing. Okay.
Patrick, if I could interrupt you for 1 second, there's one question in the chat.
Okay.
What controls the width in the previous slide?
The width, yeah. Yeah, it just have to be narrow compared with the assumed, I think, coherence length. Yeah, so you mean, oops, wrong direction. Yeah, that's a good question. You mean here, right? Is that question?
No,
Chandra can clarify, yeah.
Then I think go on further.
Yeah, no, I'm sorry.
Further.
This one.
Yeah, in the conductance plot at the bottom.
Yeah. Oh, you mean this gamma?
Yeah.
Yeah. This is controlled by the tunneling matrix element square. Right.
So
the tunneling matrix element control the width.
Times some density of states.
Yeah, the usual. Yeah. Okay. Yeah. This is the usual width. The width due to tunneling.
So do you have estimates of this?
Oh, it depends. It depends on how good your barrier is. It can go. It can change this by a lot. Yeah. I'll show you data.
Okay.
Okay. Right now. Right. So this is a probe of the coherence of this thing, and there's an additional bonus because you can see that if you go all the way from the left to the right, I have to go again through these two Majorana as stepping stones. So the tunneling probability has to do with the product of these two Majorana operators. Now it turns out this is the product of these two Majorana operators is exactly this Fermion parity operators. It's a easy mathematical demonstration. Okay. So now you have this marvelous situation that if you can measure the tunneling amplitude, then you can actually determine this fermion parity, right? In other words, depending on whether this fermion that's living there is occupied or unoccupied, there will be suddenly phase jump by pi of the transmission amplitude. Of course, this thing we can, in principle, measure with a Aharonov-Bohm loop, for example. Okay, so this will be a very important thing. So I think these are the main ways we can interrogate the Majorana. Okay, the first step is to look at one, and I think the more important step for the future is to look at two, because and I think this is where we are. I think there's evidence that we're seeing this thing in one, maybe, but if you just see it in one, you can never be sure, right? So to be sure, you have to do the next level experiment, and I'll tell you where we are. Okay. Now, the second question is why? Why are they interesting and useful? And Joe has already alluded to this because so we take two Majoranas to make one fermion, so it takes two n Majoranas to make n fermions, and therefore the Hilbert size of the Hilbert space is 2d to the n, which is much smaller than if they were fermions. Now they chose, so if I have two n Majoranas to describe the Hilbert space, I can group them in 2 by 2, in twos, and each of them is one fermion. But this grouping is arbitrary, right? What is for me to tell? I group, 1 and 2, and so on, so on. And different grouping obviously correspond to different bases, and therefore it's a unitary rotation of the Hilbert space, or the total Hilbert space. So it's not that surprising that by exchanging two Majorana, which is just a relabeling, that at least would lead to rotation of the Hilbert space. And this is the non-abelian statistics. To make this concrete, and this was what led Kitaev to propose that this would be a good quantum computer. Okay, so the qubit is actually made up of 4 Majoranas on one island. Okay, we need 4 because if I put them on one island, the total fermion parity is fixed, right? I can either have odd number of total electrons or even number of total electrons. I cannot have both, right? However, out of the 4 individually, I can have both of them unoccupied or both of them occupied, right? So I have 2 possibilities. So I can make this my 0 qubit and this is my 1 qubit. Oh, you can say, well, here I have 2 extra electrons. Of course, what you mean is that I take away a Cooper pair, okay? So these would be the 2 fermions, 2 qubit states that I can make out of 4 Majoranas, okay? So here's my 4 Majoranas, 1, 2, 3, 4. I choose a convention where I group these two to form one fermion, these two to form one fermion. And in this state, this is empty, this is empty. In this state, this is full, this is full. Okay, is that clear? Now, it turns out that if I just exchange 1 and 2, if I start out with this state, 0, then I rotate it to a superposition of this one and this one. Okay, so this is very mysterious, magical, right? Because all I have done is to switch the position of these two identical particles. How is that possible? Well, this is really because these are not states. It takes 2 of them to represent one physical state. And so from that point of view, it's not so surprising. Okay, so actually, I think all these things are actually not that mysterious once you are willing to accept the fact that I can somehow make these fermions, MZMs, as far apart in space. So now the quantum computing. It turns out that the set of operations alone is not enough to give you universal quantum computing. The set of braiding operations, as you saw before, is kind of discrete. I can rotate them only to this superposition different by I. It turns out that they cover the Bloch sphere. So you have a qubit. We can represent the phase space with Bloch sphere. It can only cover 6 points on the Bloch sphere, which is kind of feeble. Okay, and now the computer scientist tells us that if you can cover 6 points of the Bloch sphere, and you can measure these fermion parity, then you can do what they call the Clifford operation on 1 and 2 qubits. So these are some rotation of 1 and 2 qubits. Now, what Kitaev and Brafi pointed out 15 years ago is that, so this is what a Majorana computer can do for you, Clifford operation. That's all it can do. And there's a theorem that says the Clifford operation is never going to be any better than a classical computer. So that seems like a hopeless game. But they've proven a very interesting theorem that says all you need extra is to have the ability to make what they call a magic state. And this is a magic state. So you take this line, you draw a line to the middle of it and extend it to the surface of the sphere. And this is what they call a magic state. And there's just a superposition with an angle pi/8. So this angle is pi/4. Okay, right? So they tell us that all you need to do is to supplement this Majorana computer with one state, with the ability to create these magic states. Now, there are some additional key ideas that make it work. There's a very nice paper that shows that the outcome of this braiding operation, which is kind of feeble, it's only the few rotation. So it's not surprising that these can actually be replaced by a series of what is called force measurement. So force measurement is projection in the qubit space. So in other words, if I take any point in the Bloch sphere, I can project to the. If I make a measurement, I can project it to either the North Pole or the South Pole, right? Okay. So the claim is that we don't need to do braiding actually. All you have to do is to be able to make these projection measurements of the parity. Okay. And the second statement is that this magic state can be distilled by making a series of measurements with a few additional qubits. So in this way, you can imagine designing a Majorana computer just with measurements alone. So that's the idea. Okay, so the current ideas on qubits and computer architectures are based on measurement protocol rather than braiding. So the measurement of this fermion parity is key. Okay. What are the sources of error?
Patrick, let me just interrupt a second, just to be mindful of time. We were hoping to, at about 1:20, move from the seminar to like an open discussion. So
yeah, I need about, let me go to 4:30. I'm going to violate your rule. Okay, I try to stop at 4:30.
Well, let him keep going.
Yeah, keep going. I started 2 minutes late while Joe was fumbling with his computer. So I'm going to go to 4:32. No. Okay, I'll keep going and I'll stop. And then you can ask me questions. Okay, what are the sources of error? Well, the one source of error is quasi-particle tunneling. Even odd is important. So at the minute the quasi-particle jumps into your qubit island, you're dead, okay? But I think the most serious error is thermal excitation. If I can excite to an extended state in my island, then I can switch my parity on 2 of the qubits. And so this will give rise to an unwanted flip of my qubit, okay? So this is your ultimate limit of your computer. So they tell you that it's topoligically protected, but it's not 100% true. You're not protected from thermal occupation. So I think this is going to be the killer. Now, generally, this E0 is the activation energy to the lowest extended state. It's generally a fraction of the superconducting gap. So the idea would be to use a superconducting gap that is as big as possible. You want to use as high as TC as possible. Okay. Yeah. Finally, there's measurement errors. But since we're looking for discrete, even or odd answers, maybe that's not so bad. Okay. So far, I hadn't told you where to find them. Okay. So in all this time, I covered 2 of my 4 topics. Where do I find them? Well, we don't have P plus IP superconductor in nature. But fortunately, Fu and Kane came to our rescue. 10 years ago, or 12 years ago, there was a newly discovered topological insulators. And it was shown that on the surface of a topological insulator, there's a single direct surface mode like this, right? So by now it's well known, okay? Now this has the property that there's a lock momentum and spin momentum locking. So the spin is going around in circles. So they have this clever idea is that if you just couple this with a conventional superconductor, you couple the surface state with a conventional superconductor, then this winding of the spin gives you the Barry's phase, which mimic the winding of the P plus IP superconductor. So this way you can turn a conventional superconductor into effectively a P plus IP superconductor. So this opened up the floodgate of different schemes of making Majorana. So for the first time, we can imagine creating a topological insulator and using them. There's a second route, because at that time, the topological insulator was considered exotic. And so there were a number of proposals based on conventional material. They invariably involves what is called Rashba coupling, which again create this angular momentum, this spin momentum lock. But there are 2 of them. 2 is bad news when you want to make a Majorana. You always want to have odd numbers. So by applying magnetic field, you can kill one of them. And so these are the possibilities. Okay, so what are the experiments? So actually by now there have examples of going back to the original Fu and King's scheme. People managed to put topological insulator on top of a conventional albumin diselenide, and indeed they saw a 0 mode in the center of the vortex core. And more interestingly, in an iron doped superconductor, turns out that it actually also a topological insulator. So you don't even have to use proximity effect. Nature has given us a gift of something that is both superconducting and topological. And they have actually saw 0 bias peak, but they see them only in sort of half of the vortices, right? And when they plot them, they see all these other discrete states. They see this even and odd dispersion, exactly of what we talk about, right? So remember, we were saying that if you have a vortex in the topological state, you have a 0 mode, and then you have this m equal to 1, right? In another state, they have a half integer quantization, right? So they actually saw examples that look like a topological Majorana 0 mode and one that is not. The reason is that the topology is very fragile in this system. And so maybe one patch is topological, one is not. So I think this is actually pretty good evidence that they're actually seeing Majorana 0 mode. I'm going to skip that for the lack of time. Now, the bulk of the interest in the last decade is to use conventional material, and the most famous one is the indium antimonide nanowire in 2012. Now they have progressed a lot. This is the latest paper from this group. The gap is much cleaner. Originally, you have a lot of states in the gap. But still, there's controversy about what it is zero mode or not. I want to point out that this nanowire is not scalable. This is a naturally grown piece of wire, but they have now made progress by making substrate and patent this metallic gates. And they saw similar phenomenon, right, in the Copenhagen group. So I think they're really making progress on this material. The advantage of this is that, well, I'm going to have to skip all this. I should just quickly say that my self-interest that I've been working with Mudera's group at MIT. We propose another platform, which is metal-based. Okay, so it's based on using a gold 111 surface state. The advantage is that the energy scale is 1,000 times bigger than in the semiconducting wire. Okay, and we saw some evidence of this. It turns out that we put some europium island. Again, I shall defer to question and answer period. We can. And what is good is that we saw this Majorana zero mode showing up in the middle of the gap, and we saw them showing up at the same time on opposite ends of this island. This has not been done before in the semiconductor nanowire. They tried, but they never see it on both ends. So remember, the key of Majorana is that they have to appear on both ends. Okay, right. So finally, I think we really are at a stage where we should move beyond the single Majorana tunnel mode and to study the coherence of two Majorana systems. And I want to mention that they have actually made progress along these lines. So this is a interference loop that they found. That this is exact realization of what Liang Fu proposed for his teleportation. This is your nanowire. This is your superconducting wire with Majorana supposedly here. So this is one arm of the interference ring, and this is the other arm, right? So they indeed saw interference pattern as a very magnetic field flux through here, okay? They were very cautious when they wrote down this paper because up to now it's difficult to distinguish between Majoranas and just some accidental low energy states that's living there. It will be necessary to go to longer wires, but in this system, there's a limit how long a wire you can make because this is a normal wire interference. Okay, finally, roadmap to us making a qubit. These are the two papers that I like very much. They actually have a design of a qubit. So remember, a qubit would be an island that has 4 Majoranas. It turns out that if you want to do measurement, you need 6. And once you have 4, you can make 6. And then you can put them together and make a quantum computer, right? And so they were talking about using measurement using transmon technology. And we have been thinking that with our gold wire, a more practical and conceptually simpler design is to use conductivity measurement. So all we have to do is to make these interference loop of the kind that I just showed you and use a Liang Fu scheme to measure this Fermion parity. Okay. So once you do that, then you can go to town and design your qubit. And again, so I just want to show you that by turning it on and off different coupling, we are able to measure all these sigma X, sigma Y, sigma Z, the free Pauli operators, which constitute these Clifford operators. So now you can go to town and design your, I indulge and start to design my own little Majorana computer. And what you need is to be able to measure between 2 qubits, neighboring qubits, to complete this Clifford operation. So another promising direction is actually to use purely superconducting circuit. And this avoids the phase covariance problem. And this is a paper that, again, I like very much from Schrader and Fu that shows this. So finally, the last question is when? But this is a good place to summarize my talk. The point I want to make is that the Majorana fermion zero mode is actually a well understood theoretical concept. It's not that mysterious, if you're willing to abandon some of your long held notions about Hilbert space. Experimental implementation has seen steady progress. There's several competing platforms that are based on topological insulators or semiconductor wires or metals. I think we need to go beyond searching for zero bias peak. The next step is to demonstrate coherence between the Majoranas. Once you do that, then I think a single qubit is only another step away. Of course, there are many technical challenges ahead. We have to deal with errors. exponential activation, coherence time. And so it's a long journey, but there's a roadmap and it will be a fun trip. Thank you.
Thank you. So we are going to have a bit of an organized discussion, and I will copy the questions in the chat that some of us came up with beforehand. But while I'm doing that, why don't we have some questions directly on the talk? Chandra, you asked one in the chat that I wasn't sure if I'd satisfied you with my answer.
Patrick, especially at the edge, don't you have a continuum of fermion excitations as well? And would they not, when you tunnel, give you a inelastic shower?
No, not on the narrow wire. The edge is on the bulk disk.
Mm-hmm.
On the narrow wires, the edges on both sides have killed each other. Yeah, this is something that I meant to say. Right. Okay, and that's what
fire you need. Okay.
Right. You need to be narrow, but it doesn't have to be that narrow. You see, when you bring them together, this right mover and left mover can talk to each other and kill each other off. And then you have left with this. So all you need is that the width has to be narrow compared with the superconducting coherence length. So you don't actually require a very narrow wire.
Okay, thanks.
Thanks. So I did put the questions in the chat, but we'd be happy to have others as well. And one or two of the questions in the chat, I think, were pretty well answered in the talk, as it turned out, like the first one. At least there were some very nice pictures of your future quantum computer. So are there more? I mean, and also during the discussion, we certainly hope there'll be additional questions and comments from the audience. So I'm not seeing any Zoom hands raised, so people can shout something out or put it in the chat, or otherwise maybe we'll get started with the planned questions.
Oh, I'll shout something out. This is Mike Cromie. Can you hear me?
Yes,
Yeah.
but you're a little quiet.
Oh, okay. Is it better now? Patrick, I just was curious if you could just make a comment on the Ali Yazdani spin chain Majorana fermion, and also or also his bismuth edge state.
Yeah, so I meant to talk about the bismuth edge state. Yeah, the iron thing. Well, you see, for this talk, I tried to concentrate on things that are scalable, right? So for people in the audience who didn't know, Yazdani about 5 years ago, or 10 more than that, was able to find places where iron atoms, individual atoms, were arranged in a row, in a line, right? And he saw some zero bias states at the end. Okay, but these are kind of uncontrolled. You cannot really. And then the other end is some island, right? So you don't really have a clean wire. And the problem is that state is always there. You cannot test it. You cannot get rid of it and bring it back, right? So it's a little hard to really say that you've got it, right? I mean, it looks promising, right? So I think, and then of course it's not scalable at all, right? It's a kind of one-shot thing. So along those lines, there are actually more sort of advanced work recently. Wiesendanger in Germany, they actually managed to, by manipulation, make a wire of individual atoms that is like they're like 20 or 30 or 40 atoms long, and try to study tunnel at the end. And at some point, he was claiming to see something, but now I think he's getting a little cold feet. He's worrying about whether he's seeing conventional, so-called Shiva states, because it's hard to distinguish them. Okay, but I think they're running into the same problem that everybody else. They look nice, but if you really want to be, careful, it's hard, right? So that's why I think this zero bias peak is only the first step, right? It tells us, where there's smoke, right? And we have to go in and investigate. Now, the other one is actually very interesting. This is the very recently, 2 years ago, they saw this in this. So this is now based back to the topological insulator idea. So we're not doing, conventional material. And there's this idea that you put bismuth 111 on top of niobium, which is superconductor, and you build another layer, 2-layer stick of bismuth. And theory predicts that there are these things which they call hinge state that lives on the edge of this thing. And they lives only on some edges. So they live alternatively like this, okay? And now they put a blob of iron cluster here. And so this is the interface that you're looking for, right? So remember, this Majorana zero mole typically happens at the interface between a superconductor and something else, right? So they put an iron blob here to create a gap due to the magnetism. And then they indeed see evidence of this zero bias peak, okay? They don't see the partner, and they argue that it's somehow, swimming around over here. But
Yeah, that's actually a good.
I think this is kind of nice. That's very nice. Yeah.
I think that leads well to the next question in the chat is, has anyone observed a clear parity, Fermion parity measurement? Or maybe in general, that connects to one of our pre-planned questions, which is, what are the next steps beyond zero bias peaks?
Right. No, I think the short answer is no. So this is the closest that have come. So again, I recommend you to take a look at this paper, right? And okay, so before that, there are the following kind of experiments. You can make an island, right? So this is kind of like this. Suppose you turn off this other arm, right? Now you can plot the conductance through this wire as a function of gate voltage, right? So this is classic experiments.
Patrick, are you drawing something that we're supposed to be able to see?
Oh, you cannot see my
I cannot
pointer?
see it. Yeah, I'm sorry. Are you sharing?
Oh, okay. Because I have to switch. Okay, let me see. I have to switch setting again. Is it better or worse?
I cannot see it. I cannot see. I don't think you're sharing.
You're not sharing.
Oh, I'm not sharing. Oh, okay. What happened?
Didn't anyone ever teach you to share?
I did share, but
Just kidding.
I did not unshare, so I don't know what happened. So now how do I get back? I have to go back to.
Okay, let's see. Yeah, I don't know why it stopped either, but go ahead and try sharing again.
Okay, I think I have to quit this to share. So let me quit this. Yeah, this is what I'm afraid of. That's the trouble with having two.
Okay, well, in the meantime, there's one question in the chat that I can answer, which is, what are the main groups working on this? You mentioned Copenhagen and Delft. So the Copenhagen group is moving in part back to the US. Charlie Marcus, I think, is going to have a lab probably in the Seattle area.
Really?
There are, yeah, that's one bit of news. So there are a number of efforts in the US. I mean, one large one is of these 5 giant new Department of Energy quantum centers, the one led out of Oak Ridge Lab has a large focus on topological materials. So there's a lot of work there, and Los Alamos as well. But that's kind of ramping up. And then, of course, yeah, Ali Yazdani in Princeton is a group that was mentioned, and there are certainly a few others.
Okay, now I'm, what am I going to do? Maybe I should just shut down my thing.
Maybe if we, I mean, just for lack of time, Patrick, let me ask you another question. So if there's a message you want to give to the people who are primarily concerned about how to build and operate a quantum computer,
yeah,
about the current state of approaches to Majorana fermions, and you know, what aspects of the architecture of a computer are sort of going to be automatically taken care of and which aren't? I mean, what's the takeaway message for a computer scientist about the Majorana fermions?
Can you ask? I think I'm back in business. Am I? Can you see my screen now?
Yes, we can.
Yes.
Okay. Okay, so that makes it easier. Okay. Right, so let me go back. Oops. Right. So I'm back in business. Right. So the question is what again? So you mean from? Can you repeat? I was kind of distracted. Can you repeat?
You were in the process of answering one of my Chromie's questions. Then I butted in, and I butted in with this question: if there's sort of takeaway messages that you would want, like a quantum computer scientist to have about the state of Majorana fermions and maybe how a Majorana-based quantum computer would be programmed and operate, what would be the message you want to convey?
Yeah. So this is this measurement business, right? So I think the current thinking is it's all going to be a measurement-based quantum computer. So we're going to have qubits. Yeah, so this will give me an opportunity to explain a little bit more, right? So we're going to have these, the qubits will be, for example, what they call tetron, right? So this will be made up of 2 Majorana wires that are connected. So there will be 4 Majoranas here on these corners, okay? Right? So because they're two wires, okay? So actually it's this. So now, for example, to the quantum operation, I have to measure a sigma z, right? A sigma z operator, right? A sigma z operator is the question whether this pair Majorana state is occupied or empty, right? So I have to measure this pair. So I can arrange it so that I can measure this, okay? So the operation would be, I can turn on this pair. I can turn on this pair to do tunneling. Then I can measure a sigma y, a sigma x. I can make something a little bit more complicated, turn on 3 of them. I can measure y. So this is how I measure the operators sigma x, sigma y, and sigma z, okay? And the protocol is that, so here I'm just referring to the, wait a minute, what happened to my, to the statement from the Microsoft theorists, basically, that we, instead of braiding, we're going to make a series of measurements, right? So we make a series of measurement of different combination of these Majoranas, measure the sigma x, sigma y, sigma z, and that will be the entirety of my measurement, of my manipulation, okay? And the claim is by doing that and by having a magic state, which I create on a separate bunch of Majorana, then I can do universal quantum computing. Okay. Of course, I have to do this measurement fast enough so that I can do many of them within the coherence time. Right. So the coherence time is going to be a big issue, whether I can, I either have to make it very long or I have to make it measure very fast. Okay. So that if there's a showstopper, that will be it, right? But the advantage is that you don't have to worry about crosstalking or any local noise, right? Because my Majorana is protected. I can hit one side of this thing with a sledgehammer, and nothing will happen to my stored information. So my information is purely stored in this Fermion Parity, right? Which again is just the question of whether there's a fermion living here, right? Whether that fermion is occupied or unoccupied, right? And in general, I would have a linear superposition on this qubit. There will be a linear superposition of this one occupied, and this one empty, right? So that's my qubit. Okay, and this is how I address the qubit by tunneling into it and measuring the current interference loop and measure the parity. Okay, so it's I think there's a well-formulated protocol, right, of what to do, right? Whether it's realistic, that of course we don't know, right? But I think the first step is to do this, right? If you can do this, then you can start talking, right? You need to be able to tunnel all the way, to do this teleportation, go from here to here, and show that this is a phase coherent operation, that this is phase coherent. Okay, and I think this is not far away, possibly. Right? As I said, the Copenhagen group has already, they have built a device that will attempt to do exactly that.
Yeah.
And they have seen interference pattern. Okay.
So we wanted to, at the end of each of these seminars, reserve some time also for the students and postdocs to interact with the speaker. So maybe I will again barge in mind of the time. As one of the graybeards in the audience, let me thank Patrick and also Joel for a great presentation. I learned a lot. And then we have a few of the postdocs who have been kind of organizing this. So I'm hoping they will stay on. But maybe everybody else who's now past the postdoc stage can just log off. So thanks, Patrick. Thanks a lot.
Welcome.
Charles, I see you, so I'm going to assume you've got this.
Sure.
Okay, thanks. Thanks a lot, Patrick. That's great.
Okay.
Let's see. So got lots of people.
Yes, I'll go ahead and leave so that you aren't inhibited by non-postdoc types. But Charles, do you have everything you need?
I think so. I mean, I think now we just sort of have a student and postdoc conversation with Patrick. So
great. Thank you, Patrick. Thanks.